Hi, I'm Steve Saviak from the University of Cambridge, and in collaboration with Uze Amir from Purdue University and others, we present Petalute, a novel sequence of a rosette trajectory for fast flexible contrast in preclinical imaging. Petalute is an ultra-short echo time sequence that's very efficient in terms of time, signal to noise, and incoherence. It can be accelerated a lot. If we have a look at the trajectory, there are two important parameters, omega-1 and omega-2. If we fix omega-1 for the moment, so that within a shot we just reach the edge of K-space, when omega-2 is 0, we would have a radial sequence. As it increases, it looks much more like a spiral sequence, and indeed the rosette trajectory is a hybrid of the two. For this work, we've set omega-1 to be equal to omega-2, and we choose omega-1 so that we get to the edge of K-space, but then come back again so that we sample the center of K-space twice within each shot. The novel aspect here is that we reconstruct those two parts of the petal into two different images, thus having dual echo contrast. Whole K-space coverage is achieved by varying beta to flip around xy and by varying phi to go around the z-axis. We're motivated to do this because of very promising results from clinical applications in humans, looking at sodium imaging, pulmonary imaging, magnetization transfer imaging, and very importantly, spectroscopic imaging, particularly with phosphorus, where you need a wide spectral bandwidth, and that means you have to go fast, and you need to have the signal to noise to be able to do that. To understand the contrast, preclinical applications are very important, so we can do this for translational research. So we've implemented this quite in a versatile way, Paravision 6 and 7, where we can run any of the rosette trajectories in a sequence where everything's calculated on the fly with corrections for discretization, allowing for extra sampling at the K-space center, smoothing the trajectory to be kinder to the gradient, and fudging the end of it to make sure the gradient moments balance. We've applied this in a range of things already, for example in bone imaging compared against zero echo time sequences, we get higher signal to noise and higher resolution, so it's very promising. We've shown that the sequence is insensitive to motion. Here is free breathing abdominal T1 mapping with variable flip angles achieved in about 2 minutes. This is in a mouse. Here is an example of phosphorus spectroscopy where we get an incredible 1 mm isotropic resolution in just 48 minutes. We've got a spectral bandwidth of 6.5 kHz, which you wouldn't be able to get with other methods. Here we've used a technique in brain, this time with semi-laser localization and mega editing to reveal GABA signals at 1 mm isotropic resolution. This is very useful because it means instead of plumping for one particular voxel, we can measure the values of GABA over a distributed area. With ultra-short echo time, sometimes the contrast is not very useful, particularly in brain. Here we've shown magnetization transfer preparation reveals very good grey and white matter contrast. It's particularly interesting in exploring ultra-short T2 star components of that signal. So I hope this gives you a flavour of the potential of this sequence. We've demonstrated it's fast with flexible contrast, and we've shown a range of applications. We hope this will give us better understanding of complex structures and physiology in health and disease. Thank you very much.